Okay, to- in this chapter, we'll study something called static equilibrium and another subject related, sort of unrelated subject, elasticity. Okay. So only the first half of the chapter is static equilibrium, and that'll become an entire course for you guys. Okay. So here's the idea. Okay. We'll use, okay. So, for instance, here's a ladder leaning against the wall. Okay. I'm going to give you a couple of examples. And as you climb up the ladder, now we put you on the ladder, and you're climbing up the ladder. Okay. What is it that you want? As you climb up the ladder, the forces and torques on the ladders are changing. But you don't want the ladder slipping. You want this system to be in static equilibrium. Okay? You drive over this bridge, you don't want the forces and stresses on this thing are changing. You don't want this falling. Okay? So you want your structures, there are a lot of structures, you want them to be in static equilibrium. So here's the word, where the word comes from, or the phrase comes from. So static equilibrium. Static means velocity is zero. Equilibrium means acceleration is zero. Okay? Okay, so equilibrium means acceleration is zero. Acceleration zero doesn't necessarily mean velocity is zero. So you want both of them to be zero. And so you want your bridges to be in static equilibrium, you want your buildings to be in static equilibrium, and so on. Elasticity, okay, so let's go back to that example of the bridge. Okay, so let's say the bridge was empty and then you drive over the bridge. As you're driving over the bridge, what happens? You've added weight and these cables stretch ever so little. Okay, and once you drive away, if the cables didn't go back to their original shape, then the bridge will keep, over time it would keep lowering, the span would lower, and pretty soon it'll be hitting water. Okay, so you drive over the bridge and the cable that stretched went back to its original length. That's called elastic behavior. How many times do you want that to happen?
All the time.
I'm sorry?
All the time.
All the time. Okay, so you want your structures to behave elastically. Okay, so we'll talk about it. So that's what this chapter is about. All right, so static equilibrium. Okay, so here's the deal. Okay, so now let me start off with an example. So whenever we're talking about static equilibrium, we're talking about forces applied to extended objects. So let's say this is a uniform bar, and I apply a force of 10 newtons like that, and 10 newtons like this. What will happen?
Nothing.
Nothing. Okay, this thing is at rest. The total force is zero, and nothing will happen. Again, 10 newtons and 10 newtons. The total force is zero.
Oh, nothing.
Nothing will happen. It will rotate. Okay, so if you want static equilibrium, in all these cases, the sum of the forces was zero. Okay, So when you're applying forces to extended objects, just this condition is not good enough. What you learn is, what you also want is the sum of the torques of these forces need to be zero. Okay? And that's when you'll have static equilibrium. So when you're applying forces to extended objects. And these two courses are the foundation for this entire course, the static equilibrium, just those two. Yeah. Okay, so you'll apply those two equations to various situations. And then you saw elasticity is, you stress an object, it deforms, and when you release the stress, you want it to go back to its original shape. Okay? So those are the two topics we'll talk about. All right, so we'll define center of gravity's conditions for equilibrium and so on. Okay? Then we'll do stress, strain, and elastic moduli. Okay. All right, so here's you're preparing to bowl, and right now you want this to be in equilibrium. There's this weight, and there's the force applied by your muscle on this bone and so on. Okay, so we'll come to that. All right, let's talk about center of gravity. This is different than center of mass. Okay. These 2 points will be the same for small objects. But for very large objects, and you have to have very large objects like say Mount Everest, then the center of gravity will be different than the center of mass. Okay. So if this were Mount Everest, there's the center of gravity, and the center of gravity is the point at which you can think that the weight of the object is acting. Okay. So if this were Mount Everest and there is Earth, center of mass will be above center of gravity. Center of gravity will be closer to the Earth. Okay. For a small, let's say uniform square object, the center of mass and center of gravity will be right, the same point will be at the center. Okay. All right, so center of gravity is the point at which the weight of the object is acting. And for small objects, center of mass and center of gravity are the same. So for a bowling ball, the center of mass is at its center, and the center of gravity is at its center. Okay? And so on. All right. Center of gravity of an object like this is the balancing point. Okay. All right. So the gravitational force of a body effectively acts at a single point called the center of gravity, and that's why we want it. Okay? Because we'll be using this in our problems. Okay. Here is the formula for the center of mass. The center of mass is you break this object into little pieces, m1 times, this is the x-coordinate of the center of mass, times the x-coordinate of that guy, m2 times the x-coordinate of that guy, and you add over all the pieces and divide by the total mass. That's the center of mass. If you wanted to calculate the center of gravity, x component of the center of gravity, then you would multiply by g1. What is g1? I'm sorry?
Gravity fields at that point.
Acceleration due to gravity at that point. G2 is the acceleration due to gravity at that point. Okay, what's the acceleration due to gravity at this point? I'm sorry? No, what is the acceleration due to gravity at this point? What is the value of acceleration due to gravity at this point?
9.8 meters per second squared.
What is it at this point?
Also 9.8.
What is it at this point?
About the same.
Right. Okay, so if you have a small object, it'll be the same everywhere. Okay, that's the.
So the only way center of mass, center of gravity are equal is if it's not the same density throughout. Like
No. If it's a very large object. So, okay, so G is 9.8 here, but if you went up by 100 miles up, then G would be slightly different. Okay. That's the point. All right, so that's what this formula is. And if G is the same everywhere, then that would cancel, and this formula would be exactly that. Okay? Okay. All right, so the reason we did that, defined that was, so here's a ladder. You want to know where the force of gravity acts on this ladder, and that acts at the center of gravity. And since this is a small object and it's uniform density, that's also the geometric center of the object. And that's why we wanted to know the center of gravity, okay? So here's a ladder, and again, this ladder is leaning against the wall, and if you start climbing the ladder, what you want is that the ladder not slip. So we'll analyze all the forces acting on the ladder, okay? So for small homogeneous symmetric objects, the center of gravity as well as the center of mass is its geometric center, okay? So the center of gravity, center of mass, and the geometric center all coincide for these guys, for uniform objects. Okay, so here's your object, and what are all the forces acting on it? And normally generally we'll consider smooth walls, and so this can only exert a normal force on the ladder, which is that. There's the weight, where's the acting at the center of gravity. Here's a friction force. What kind of friction force is this? I'm sorry? A static friction force. And you don't want it ever becoming kinetic friction force. Okay. So that's a static friction force. Okay. So to ensure that you have a large static friction force, what do you do on ladders? You put a rubber boot on them on the bottom, okay? And here is the normal force. Okay. So for this ladder to be in equilibrium, what we will do is we will require that the sum of all the forces be 0 and the sum of the torques of all these forces be 0. Okay? And that's why we've drawn all the forces acting on it and the point of application, and then you can calculate the torque about any point. You'll learn that in a second. All right, this is just a pretty picture, and it's actually quite neat. Okay. Do you notice anything neat about this guy?
One of the blocks is entirely over the edge.
Yeah, see, the stop block is entirely over the edge. Yeah. And so here's how you do this. Okay. Now, for this thing not to fall down over the edge, what needs to happen? Huh? The center of mass needs to be behind the edge. Okay. So you see the center of mass of this guy is behind the edge. And for these two not to topple, the center of mass of these two guys has to be behind the edge of this guy. There's the center of mass of these two guys, and it's behind the edge of these guys. For these three to not topple, the center of mass of these three guys, which is there, is behind the edge, and so on. Yeah. So this is fairly neat. And actually, oops. So this is a physics demo lab in Harvard University, and this guy's in charge. This guy's in charge, and he's fairly proud of it. Yeah. So this is not crazy, look. Okay. So all you have to do is for each floor, the center of mass of each building had better be on the footprint of the floor below. Okay. It's a beautiful building. All right. So we had this wine bottle holder. And again, what's happening here? There's the footprint. So for this thing to balance, the center of mass has to be right above this footprint. Okay? So if an object is at rest, then it's in static equilibrium. When the acceleration of an object is zero, it's said to be in equilibrium. But when your acceleration is zero, you don't necessarily have to be at rest. Your velocity can be constant. If your velocity is constant, that's dynamic equilibrium. Okay? What we are interested in is static equilibrium. So what we are interested in is A equal to 0 and V equal to 0. Okay? All right. So here is so the conditions for equilibrium. Yep.
I was asking about the last one.
I'm sorry?
I was asking about the last one. Do the weights have to be similar, or
Which one?
both of them? Both the wooden
You're talking?
stick, the wooden stick and the bottle.
Oh, no. So I guess roughly half, you can think of this, half the weight of this thing is there and half. Well, no, so in a seesaw, if you have a light person sitting on the far end and you have a heavy person, the heavy person is closer to the fulcrum. That's all. Yeah. So this is heavier and it's closer to the footprint. Yeah. All right, so the condition for when forces are applied to extended objects, the condition for static equilibrium are these two conditions. The sum of the forces should equal 0, and the sum of the torque should equal 0. Okay, so. Okay, that's the conditions. Right, so in this diagram, this is sort of a misleading picture deliberately. Are all these penguins of equal weight? Okay, so let's say if this is D and this is 3D, that's the distance from the point of suspension. Okay, for this to be balanced like this, what needs to happen is the center of mass of this guy is right at this point, at the point of suspension. And so if this guy is M, this guy has to be 3M. 3M times D equal to 3D times M. Okay? So this torque is equal to this torque. The clockwise torque is equal to the counterclockwise torque. All right, so these two combined are 4M, and then 4, so these two combined are 4M. 4M times 3D should equal this times D. Okay, so this guy is 12M. And then 12M times 3D equal to this times D. So that's, this guy is 36M. So next time you see, if you go to art shows, you'll see a lot of these types of displays, and those masses are quite different. You know. All right, now when you do a static equilibrium course, then the forces will be in 3 dimensions and stuff like that. But for starters now, all the forces we'll restrict the forces to be in 2 dimensions. And so you'll have X and Y component of the forces, and the torques will be in the 3rd dimension along the Z-axis, okay? So we will have only 3 equations to solve for, okay? And that's how we'll set up problems. Okay, so our forces will be in 2 dimensions, and our torque will be in one dimension. Okay. So now this is two equations and that's one equation. All right, so here's a problem. Okay. Here's a typical problem that we want to solve. So here's a scaffold. This can be in a construction site, and this guy, he doesn't want to worry no matter where he is on the scaffold. Okay, so your job as an engineer will be, as this guy walks further out, the tension in the string has to increase to make sure that this thing doesn't fall down, this doesn't break and all that. So you have to do all kinds of calculation, and you have to make sure that this cable can withstand the maximum tension it'll bear. Okay? This hinge shouldn't come off and all that kind of stuff. Okay. All right, so no matter where this guy is, you want this beam to be in static equilibrium. Okay. So what you want to do, you want to look at all the forces acting on the beam and make sure that these two conditions are satisfied. These two equations are satisfied. Okay. So what we'll do is we'll draw a free body diagram. A free body diagram just shows you just the essential things. Okay. So whatever object it is that you're analyzing. So let's say you're analyzing this beam. You'll show just the beam and the forces acting on the beam. Okay. So here is the beam. There is the tension on the beam. Okay. The tension of this cable applied to the beam there. There is the weight of the beam. That's the force of gravity on the beam. There is the weight of the person acting on the beam. Yeah. So the gravity is pulling him down and he is pushing on the beam. And there is the force that the hinge is exerting on the beam. Yep. And so here are all the forces acting on the beam and the point at which these forces are acting, because that's important for calculating the torques. And what is it that you want? Or what is that this guy wants? That the beam be at rest at all times. And so the sum of these forces should be 0. And the sum of the torques of these forces should be 0. Okay, and that's what this chapter is about. Okay, you guys understand? Okay, now here's the deal. The torque of a force depends on what point you're calculating the torque about. So the torque of this force is different if you calculate it about this point, this point, this point, that point, and so on. How many points can you calculate the torque of this force about? Infinite. So in this equation, the question is, what point do you calculate the torque about?
The center of mass of the total object.
Okay, so choose a convenient axis for calculating the net torque on the object. Okay, so if you don't want to mess with this force, if you don't care to calculate this force, calculate the torque about this point. Okay, and that force gets eliminated. When the net torque is 0, the choice of axis is arbitrary. Okay, if the net torque is 0, then you can calculate it about any point and the torque will come out to be 0. And so you calculate it about a point on, if you don't want to calculate that force, you choose that as the point of it. Okay? But the thing is, if the net torque is 0, then you can calculate it about any point. A force that acts along a line passing through the axis produces 0 torque. So, okay, so if you don't want to calculate that torque, force, you calculate the torque about that point. So let's look at this problem. We'll look at this bone. There's that bone. Okay, the forces on this bone are the weight of the bowling ball, the force that this muscle is exerting, and this bone is pushing this bone against that bone, and so the reaction force of that bone. Now let me point out an interesting fact here. Okay, let's say the bowling ball is, I don't know, what, 15 pounds? Or we'll say 10 pounds, okay? The bowling ball is 10 pounds. And this is about almost 2 feet, or 18 inches, 20 inches. Let's say this is 20 inches. Okay, so this is 20 inches. And this is about 1 inch. Okay. So this force, F times 1 inch, should equal 10 times 20 inches. So the force is 200 pounds. To lift a 10-pound bowling ball, your muscles apply that 200-pound force. That doesn't sound like a good design to me. Why is that so? You guys understand what I'm saying?
Sorry, can you repeat the question?
All right, this bowling ball was 10 pounds. Okay, so in static equilibrium, this is a clockwise torque, which is this force times the moment arm. We're calculating the torque about this point. This is a clockwise torque, this provides the counterclockwise torque. And that torque is that force times that moment arm. That was 1 inch. This was 20 inches. So clockwise torque was equal to counterclockwise torque. So it turns out, so you do the calculation, this force is 20 times greater than this thing. You're lifting a 10-pound weight, and your muscles are applying 200 pounds of force. Sounds like a very bad design to me. So why is it designed this way? All right, your muscle can only compress a little. So for a large motion, okay, the muscle compresses a little, which will give you a large motion here. Okay. So that's the deal. A large force applied over a small distance can give you a large work. Okay. So because your muscles can't compress or extend too much, that's why you have it. That's the design. Okay. All right, now let's look at the ladder. Okay. So you don't want the ladder slipping, so there's the static friction force. Okay. So there are all the forces that's without the person there. So if you want to put a person on, then you would add the weight of the person as well. And then make sure that the sum of the forces and sum of the torques are 0. So the static friction force between the ladder and the ground keeps the ladder from slipping. Okay, and so that's where you put a rubber boot, so you can have a large static friction force. Okay. All right, we'll actually stop here because I don't want to start this and not be able to finish it, and I don't want to rush through it. So what is today? Thursday. Okay, Tuesday we will finish the lecture and then problems from this chapter. Okay.